Climate change is one of the most urgent challenges of our time. Greenhouse gas emissions are increasingly altering our ecosystem. But what if we could transform these gases into a valuable resource? The goal of the HYSOLCHEM project is to find a solution to one of the most pressing issues of our time by turning waste into resources. How? Through an affordable photocatalytic reactor that converts carbon dioxide into fuels while reducing water pollution. The reactor uses advanced photo and electrocatalysts to transform carbon dioxide into high-value compounds such as methane, ammonia, and ethylene. It also oxidizes and organic pollutants in wastewater, contributing to a fully circular and zero-impact production cycle. The process is circular and entirely carbon neutral, since the degradation of wastewater pollutants supplies more carbon and nitrogen which are used as oxidants in the reaction. The HYSOLCHEM photoreactor is designed for municipal wastewater treatment plants, but it can be adapted for installation in the water treatment train of carbon-intensive industries, chemicals, refinery, cement, fertilizers, and energy producers. This achievement was made possible through the integration of diverse expertise aimed at tackling sustainability challenges. The reactor, developed by the HYSOLCHEM team, features 3 innovative components: anodes, cathodes, and membranes. The photocathode is responsible for carbon and nitrogen reduction and fixation in energy-rich compounds such as hydrocarbons, effectively driving the process of artificial photosynthesis.
So the work that we have been doing in the photocathode side is developing hybrid photocathodes, mainly based on copper-based metal oxides and also in conjugated porous polymers. And we have been developing different structures, mainly based on copper 1 oxide, copper 2 oxide, and also copper bismutate, and also employing different conjugated porous polymers, as for example this carbazole.
The dark anode is responsible for the oxidation of pollutants in water. Electrochemical advanced oxidation processes are considered efficient and environmentally friendlier than other methods.
I have been working on the anodes of the HYSOLCHEM project. I have been trying to mix different metals to prepare some multi-metal oxides anodes for the project. I have been working on different structures like LDH, high entropy materials, to get some high efficiency anode to remove organic pollutants from wastewater.
Traditional cation exchange membranes use a perfluorinated membrane polymer. This polymer has a high environmental footprint and is a persistent pollutant. HYSOLCHEM makes membrane production more sustainable by using non-fluorinated materials.
The objective for our team was to design, to fabricate a cation exchange membrane that can serve in the HYSOLCHEM process. Now I have to say, this team I consider quite a dream team because we have the academic insight as well as the industrial insight. We worked on 2 different concepts. Here at the KU Leuven, we were more focusing on homogeneous, self-supporting cation exchange membranes, and at Ambercel they had their own innovative concept of a layer-by-layer hierarchical cation exchange membrane. The results are good. The 2 concepts that we designed were both competitive in performance, and we emphasized a lot on the sustainability aspect of our membranes. At the KU Leuven, we were working with green organic solvents and non-hazardous materials, and at Ambercel, they were focusing on eliminating the use of the solvent in general to make their functional layer.
To ensure uniform distribution of current and potential, lower internal resistance, and enhance the transport rate of electroactive species to the electrode surface, an expanded graphite plate was strategically positioned in the internal blocks, holding the anode centrally in the analyte channel.
The main objective is to design and upscale up to Tier 5 a hybrid flow photoreactor for the reduction of CO2 and nitrogen to produce fuels and chemicals, coupled to the electroxidation of microplastics and organic pollutants from wastewater treatment plants. The idea is to combine both clean technologies, CO2 nitrogen reduction and water remediation, in a single device in order to reduce the cost of each conventional device separately. The concept is being applied to municipal wastewater treatment plants, but It must have the potential to be installed, for example, in distributed water treatment units next to intensive industries or energy producers, housing, or even any other portable or stationary locations.
The innovations implemented have been tested in various contexts with exciting results.
So what I'm holding in my hand is an electrochemical cell that was specially designed to be used at our beamline to use synchrotron light to study the chemical composition of the cell. And we are lucky today because the beamline is actually not operational and we could take it apart. So what's actually happening is we have an electrochemical cell with a membrane. The membrane is missing at the moment, where we deposit the electrocatalyst. Now this catalyst can be brought very close to our electron analyzer here. So the cone that you see here is the front end of the electron analyzer. The pipe that you see here is the back end of the beamline, so synchrotron light comes from here. The electrons that are emitted from the electrochemical cell enter a very small hole at the front end of the analyzer, and this is how we then can do photoelectron spectroscopy on our electrocatalyst in operation.
Our main role has been the validation of the project prototypes under real environments using our own wastewater treatment plant for testing the final prototype and the intermediate prototypes. And probably this is the main challenge we face in the project, because the scaling up and the settling of the prototype under real condition has been really challenging. We have been also focusing on the application of computational fluid dynamics simulation for the optimization of the electrochemical cells, and this is one of the key results from our side, because we prove how the use of CFD simulation can significantly improve and make more efficient the design and optimization of these systems without requiring significant experimental information.
The HYSOLCHEM project, carried out within the Horizon 2020 program, started in 2022 and is going to conclude in April 2025.
By the end of the project, which is April 2025, HYSOLCHEM has generated 19 key exploitable results. Those are discrete pieces of technology that can be used for different applications in electrochemistry. We have, for example, 3 different kinds of photocathodes, 5 different kinds of anodes, 3 different kinds of membrane, and a customized photoelectrochemical cell that has been used for testing at a synchrotron. These results, they are all more or less at technology readiness level 5, which means that they have been demonstrated in simulated condition in a laboratory controlled environment, and they are essentially ready for industrialization. All these results together, they converge in what we can consider the cusp result of the project, which is a fully functional upscaled prototype of a photoelectrochemical reactor. This reactor does 3 things: artificial photosynthesis, meaning that it captures carbon dioxide from the atmosphere. It can use this carbon dioxide to create high-value products such as fuel, and all the while it's capable of oxidizing pollutant in wastewater, such as phenol, for example. The next step for HYSOLCHEM is the industrialization of the photoelectrochemical reactor and of the individual results, as well as the validation of the business model. We think that the reactor could find an application in the wastewater treatment train of an industrial process.
With the support of the scientific community, the project aims to revolutionize waste treatment and sustainable energy production. Join the shift towards a zero-emission world.